Hi everyone. In this experiment, we're going to determine the molar mass of oxygen gas. And I did the experiment myself, which was kind of interesting, kind of fun. Uh, but the setup is the diagram, and the picture of the setup is in this slide. You can just see, we've got potassium chlorate, Bunsen burner, and the idea is that we're going to displace water when we produce the oxygen gas. And so watch the video of me doing the experiment on the next slide. And then on the last slide, I'll talk about how to do the calculations. Hey everyone, so I'm going to record this experiment with my phone. Hopefully you can hear me. Hopefully I can perform the experiment and record it at the same time. So I just wanted you to be able to see this reaction a little bit. So you can see here I've got potassium chlorate in the test tube, and it's connected by a tube to this flask. And then in the flask we've got some water, and then another tube going into a beaker. And I've set up a siphon here. So the idea is the potassium chlorate is going to decompose, and it's going to produce oxygen gas. And that oxygen gas then is going to push water from this flask into the beaker. So whatever volume of oxygen gas is produced, that volume will push the same amount of water into the beaker, and then we can measure the amount of oxygen gas that's produced. All right, so I've got the Bunsen burner lit. I'm just going to start heating this up, and you'll see as we go here, and I got to be really careful not to overdo it, but you're going to see it's going to start to melt. Hopefully you can see that there. You can see it melting a little bit. And then it's going to start bubbling. Now it's not really boiling. It's producing oxygen, right? So the oxygen is forming the bubbles as it comes off. So you can see it's almost all melted now. There's some bubbles. I just got to kind of go back and forth a little bit, not heat it too fast. And I'm keeping my eye on the beaker over there to see the water that's being delivered. And I just got to take it kind of easy and not make it explode and shoot this cork across the room. So can you really see it bubbling there? Okay. And then once I get some water going over at a decent rate, I'll switch my perspectives here. This is a challenge for me to kind of do this and talk and video record it with my phone and make sure I'm not doing it too fast, because I've never actually done this experiment before. I've watched hundreds and hundreds of students do it. Okay, so now I'm just going to kind of go over here and record the water coming as I continue to heat it somewhat gently. So you can see it's starting to fill up with water. So I'm just going to go until I collect about, what did it say, 300 milliliters or something like that. That's working pretty well. Now I'm getting it going pretty fast. I don't want to do it too fast. But you get the idea, right? Water's coming over. This is all decomposing. And away we go. All right, so hopefully that was fun, or at least it's not as fun as doing it yourself, but at least now you can see it and you get the idea when you do the calculations in the lab. Otherwise, it's just like doing a homework problem, which is, we've got plenty of those. So that's the lab. All right, so now that you've seen the experiment, we're going to do the calculations, or talk about how to do the calculations. And I don't actually do the calculation for you. What I want to do is just kind of give you an outline of the experiment and an outline of the calculations, and then most importantly, if you have questions about how to do the calculations, please post those questions to the discussion page set up on D2L just for this experiment. So you can see the idea of this reaction is that we heat up this potassium chlorate. It decomposes, and when it decomposes, it gives off oxygen gas. We can collect that oxygen gas over water. So it's displacing water, and the volume of water that is pushed over into that beaker is equal to the volume of the oxygen gas. So that's how we measure the volume of oxygen. Now, there's a calculation just like this in your book. In fact, this textbook, I believe they do the same exact experiment in there as one of their examples of getting the molar mass. But I maybe don't do the calculation exactly the same way that they do, because what my goal in having you do the calculations is something that would be more long lasting, something that you wouldn't have to memorize some steps to do something. And so what I want you to try and do with calculations as much as possible is think about how you can solve this in a way that you don't have to remember anything. Okay. And so, you're going to learn the material, but what you want to do is just start with the definition. And if you know the definition, and then you can figure it out. So that's what I've got, the way I've got it set up here. So you can see molar mass. I don't know how to do this calculation, but I know the molar mass is grams of oxygen over moles of oxygen, right? That's the definition of molar mass. And so in the lab, we get the grams just by weighing it. We weigh by difference, but I've got the lab report form filled out with the measurements ahead of time, because you're not, I'm doing the experiment. And so those measurements are already entered in there. I thought, well, I could take a picture of the balance and all that stuff, but there's, that doesn't really add anything to it, I don't think. I just wanted you to see the actual reaction. So anyway, we have the mass because we weighed it. We weighed it before and after. And the mass that was gone, that's the mass of the oxygen, right? And so we just need to use the ideal gas law to get the moles of oxygen. And so there's our ideal gas law, PV equals nRT, piv nert. And we're going to measure all of these values, right? So we can measure temperature using a thermometer. We have a barometer in the lab. We measure the atmospheric pressure. Now we need the pressure of the oxygen, so I'll talk about that at the end. And the barometer just gives us the total pressure in the room, atmospheric pressure. And then the volume, we just can measure the volume of the water using a grad cylinder. All right, so the note there, and this is the thing that usually trips people up when they're doing these calculations. Dalton's law of partial pressures, and it's important that we can do partial pressure calculations like this for Dalton's law. All it says is that the total pressure is the sum of all the individual pressures, right? And so we want just the pressure of the oxygen, but that oxygen gas is being produced over water, right? And it's saturated with water vapor when it's pushing that water over into the beaker. So here's the deal. You can look up the vapor pressure of water in a table that tells you what that vapor pressure will be at every temperature. So in the lab handout, there's a table of vapor pressures for water. And so you need to use that to adjust the pressure for the fact that it's a pressure of oxygen and water. And in the ideal gas law, we just want the pressure of oxygen. All right, so hopefully you then can see how you could calculate number of moles there. And the key thing here, as always in the ideal gas chapter, is units. Got to get all the units to match with, like we did in the content, with the gas constant, so that we can calculate the number of moles. And we just plug it in, and hopefully that works. Like I said, if you have any questions about this, have trouble with the calculations at all, please post to the discussion page, and I will answer those every day. All right, thanks.